So what we are going to do today, we will start with the feedback stability. Last time you have covered like a feedback amplifier and see some basics. So now we are going to talk about one of the major things in the feedback system, and that is the stability. Because in the feedback system, the one of the major challenge is to make the system stable, and that's what we are going to talk in today's lecture with the help of some examples. So initially we will start with the just generic definition of stability in the feedback system, and then we will link to the amplifier or some of the examples which we have previously seen, some similar concept of common stage, cascode, and then cascode common stage, and how we can make the system stable if it's initially unstable. If you have any concerns in between, if you have any comment, you can raise your hand and I will most likely able to see. If, for example, if I skip you, might be I'm not able to see, then you can just unmute yourself and just tell the query on your own. So let's make sure we are recording the session. We are recording the session. So generally about the feedback system, if you see on the left hand side, we have an open loop system, which we previously are seeing, where we have an input VI and an output V out, and with a gain of A. A can be a DC gain or low frequency gain, or for a higher frequency, we can also have some capacitances involved, and then this is going to be the overall open loop gain. But the thing which we previously covered, we didn't put any feedback. This means whatever we apply on input, it will get amplified and we're going to have an output. Based on whatever the supply voltage we are using, the system can get saturated, but there was nothing feedback involved in it. If we see the other side, the closed loop system, what we can have the same thing, VI and a feed forward gain and a V out, but now we have a feedback in the form of here we are putting a gain of beta and going back towards the input side to the input terminal of gain A. So we are giving a new input named VS, okay, which is being added with the subtracted component of the beta. If it's getting this, if it's subtracting with the feedback component, we normally call it as a negative feedback. But if it's getting addition component, we normally call it as a positive feedback. So this is the general definition, generic, of a negative or a positive feedback. For us, we are only concerned about the negative feedback system. Why negative feedback system? Because the positive feedback system are going to be in any case unstable. We are not concerned with that when we're talking about amplifier. That's why we're only going to talk about the negative feedback system, and we want to make sure those negative feedback systems are stable. On the other hand side, one of the common example for the positive feedback system is an oscillator. Oscillator oscillates, and that is the main purpose of an oscillator, but that is a positive feedback system. So what happens in a positive feedback system, we will give an input, something like this, and it will pass through. First round will come like this. After, when the feedback is going to go here, the signal will get amplified, or even it's going to be as it is, but it will add here in the second turn. And but the resultant is going to be a bigger signal. So after passage of time, the signal will start increasing and it will start oscillating, and ultimately it will become a very much infinite signal. So that's the main concept of a positive feedback system. But since we are talking only about a negative feedback system, so let's talk about the negative feedback and the challenges involved in the negative feedback system. So the biggest challenge in the negative feedback system, as we mentioned, is the stability. And for a stability of an amplifier, if an amplifier is not stable, we know what can happen. We are applying a very much small signal, and what we are getting is a saturated signal. We are not getting the signal itself, rather we are getting a noise. Or our environment has a pretty much huge noises. They can be very much small value, but if our system is not stable, this means the system is like multiplying that input by a infinite gain. What will happen to our output, that even any noise, very much small noise, can be in the nanovolt or picovolt range, can get amplified and can saturate our system, and our amplifier is not going to work as desired. So that's why we need to understand what is meant by the stability. The design amplifier should not show bad response. So design amplifier should not show a bad response. Bad response means it shouldn't be unstable or shouldn't be even marginally stable. So that's what we are going to talk about, the marginally stable thing. But the one thing we know, it shouldn't oscillate, meaning it shouldn't be unstable, or it shouldn't increase with the passage of time, as can be seen here in the red figure. Okay. Any concern regarding the negative feedback or a positive feedback or the oscillation behavior? If there is no concern, then we'll move forward. So if we just want to talk in terms of amplifier, this is a common feedback amplifier, a common structure like which we all are familiar from, or might be elementary school too, that we have an amplifier. We show an amplifier with a triangular shape. Ji Khan Mohammed, please unmute yourself.
सर एक सेकंड पीछे कर सकते हैं?
जी जी जी।
थैंक यू सर।
So now again talking about the common feedback amplifier. So we have this triangle amplifier, okay, which is an inverting at this case. We have two feedback resistances, R1 and R2. Okay, we have an input and we have an out. Okay, all of us know what's the gain. The gain is going to be controlled by the ratio of these resistance. So we can say V out is going to be, V out by V in is going to be minus R2 by R1. Okay, so that is the gain of the system. Previously, we were talking only about what's inside the dotted curve. Till now, we have covered like how can we design an amplifier with a high gain, with the multi-stages, with the cascade and all of those things. But we were only talking about this dotted structure. And this dotted structure has to be stable itself, but on top of it, the closed loop system, which is consisting of minus R2 over R1, should also be stable. That we are going to see today. So if you open this one structure, this is a simple common source amplifier, you can see. So everything else is the same, just we are replacing this triangle amplifier with a common source, simple common source stage. Okay. So you can see a common source stage, and we're applying an input on the gate, we're taking an output on the drain side, and we have RD as a load resistance where the gain is going to be multiplied. But before talking about the stability, what is the most important thing? We need to see that how we are going to decide whether the system is stable or no. So that's why we have to revise our scale of the Bode plot. Last time, if you remember, I guess 10 lectures back, we started about the Bode plot and we discussed about the magnitude response. Also, we briefly touched about the phase response, but we will go again towards the Bode plot and see how we can decide a system is stable or not stable, but based on that skill which is required is Bode plot. So we will talk briefly about a Bode plot now. You might also have seen the Bode plot in your feedback course. I'm not sure whether you have covered by this time, but I guess you might have covered by this time. But again, it will be just like a repetition of the same thing, but we need to still do that stuff. So for the Bode plot, I will just take this example, which in my section we did that time. We'll just revise it again. So if we have any function A of omega having G Ali.
Assalamu alaikum sir. So just one request, if it's possible, sir, थोड़ी सी speed कम कर लें. I hope I'm not disturbing you.
Okay, that's totally fine. Speed. That's totally fine.
Thank you, sir.
Okay. So we'll start from the Bode plot. Okay, we'll just make a pace small lower from the Bode plot. So we will start with the Bode plot now. So in the Bode plot, we have a function A of omega. In the A of omega, what we are having a one terminology or 1 0 in the numerator and we have two poles. You can see omega p1 and omega p2 in the denominators. Okay, so if we have some function which is a frequency dependent, having 1 0 and having two poles, okay, so we need to draw the magnitude plot, and also we need to draw the phase plot, and combination of a magnitude plot and a phase plot tells us useful information about the stability of the system. Okay, that we are going to come in a couple of minutes, but let's first see how we can draw the magnitude response. That's somehow which we previously covered, but let's see again. This is a magnitude plot. We are going to take 20 log of this A of omega. If we take the 20 log of A of omega, what's going to happen? The zeros or the numerator terms are going to be added, and the denominator terms are going to be subtracted with the multiplication of 20 log, since we want to represent in the dB scale. So in the dB scale, what we can write 20 log of 1 plus j omega by omega z minus 20 log of 1 plus j omega by omega p1 minus 20 log of 1 plus j omega by omega p2. So this is omega p2. That somehow we know, but still we need to just write how we normally write this terminology. In a couple of minutes, we will also open that how we just open this magnitude 20 log 1 plus j omega by omega z, and how we do simplification for the paper. Then coming towards the phase response do the same thing. If we have multiple zeros and poles, we have to take individual phase impact in the overall function. So what we are going to do, we are going to have the phase response of a zero subtracted by the phase response of a poles. Because the zero is coming as a numerator, poles are in the denominator, so the zero will come with the positive factor and the denominator will come as a negative factor. And how we normally write? Angle of 1 plus j omega by omega z minus angle of 1 plus j omega by omega p1 minus 1 plus j omega by omega p2, where omega is the frequency around across which we are seeing the behavior. Omega z is the frequency of a zero. Omega p is the frequency, or you can say the radians per second, and omega p2 is the radians per second for the second pole. Okay. So now let's go back how we see the magnitude response and how we decide that magnitude response. Okay. So for the magnitude response, the rule of thumb is that we need to see 2 points. The first point is the point where omega, or the desired frequency, is very much less than omega z. So for example, if I just do small plot here, if I have, this is my omega, okay, and my omega z is here, for example, at this point. So any frequency which is less than omega z by some good amount, okay, I'm writing omega is less than omega z, meaning any frequency lesser than omega z will be equal to 20 log of this omega z. And when omega z is less than omega z, and if we place this thing and find the magnitude of omega z, it's going to be 1 plus omega by omega z. And when omega z is very much bigger than omega, this means this factor, square of this factor, is going to be very much small. We can somehow approximate to 1 plus 0, and ultimately the resultant is going to be 1. And 20 log of 1 and log of 1 is equal to 0, so it's going to be 0 dB. So anything which is very much less than omega z is going to be a 0 dB for us. And what is meant by very much less? Common rule of thumb, we say if omega z is equal to, this is basically 10 times. This is normally we say if omega is equal to 10 times factor, meaning if this is omega z and anything which is less than 10 times, so it will not be this thing. Okay, so this thing, any omega which is 10 times less than omega z, we will assume that it's going to be 0. But for approximation, we are going to do this thing. Any frequency which is less than omega z, we are going to take it as 0 for our analysis. just for simplification. Since we are drawing by paper and pencil, we don't want to rely on any calculator. We don't want to rely on accurate. We just want to get a feeling about the system stability. That's why any frequency lesser than omega z is going to be considered as a 0 dB. Okay. And what about any frequency bigger than omega z? So we are going to again see a higher frequency content, which is 10 times, for example, bigger than omega z, which we previously writing omega is equal to 10 times omega z. And if we place 10 times omega z in this equation, we are going to get that 1 is going to be very much small as compared to omega by omega z. So we are going to end up with 20 log of omega by omega z. This means the slope is going to be 20 dB per decade. And in the case of 0, it's going to be in the enhancing mode. So what we can simplify, anything or any frequency greater than omega z, the amplitude or the magnitude is going to enhance by the factor of 20 dB per decade. This is case for the 0. Is this point clear to everyone? So if there is any confusion, clearly.
So could you just repeat this graph? How did this 20 dB point come up?
Okay, let me just draw it again properly. So for example, if we just have this function, and we are told to draw the magnitude of this plot. Okay, so if we want to do the magnitude of this plot, what's going to happen? We are going to 1 plus j omega by we normally do this mod. Okay, this mod means we are going to take a square plus b square. We do this magnitude way whenever the mod is. Now we are putting that analysis just for our simplification when omega is very much less than omega z. Whenever omega is very much less than omega z, what will happen with this factor? This will be near to 0. Okay. Why? We are putting that omega is 10 times because हम लोगों ने factor कर दिया था. It's going to be this thing. So it's going to be 1 over 100. So 1 over 100 is roughly equal to very much small as compared to 1. So for our simplification, we can just say this is going to be 1, and in terms of log, it's going to be 0 dB. Okay?
Yes.
Okay. Similarly, for the other scenario, when we are having a bigger case, omega is greater than omega 0, we're again having 1 plus omega by omega z. Again, putting that terminology which we were just using. So 1 plus omega by omega z. Now this time this factor is a bigger value. We cannot get rid of it, but we can get rid of 1 because this is a bigger value. If we just want to replace, put that representation that omega is equal to, let's say 10 times omega z. So it's going to be 100. So we can ignore 1 as compared to 100. This means I can safely write this thing as omega by omega z whole square, or I can write omega by omega z, 20 log. Okay, and that's what we are writing. That's what we are drawing. So when we are drawing this thing, we were saying safely that if this is omega z and this is omega, so till we reach omega z, we are saying we are at a 0 dB value because of this consideration. Okay, and as we go from omega z, starts increasing from omega c, we are following the slope of 20 log omega by omega c. So 20 factor is going to come because of the slope, and omega by omega z is going to come whatever the slope they are going to carry. So that's why we say it's like this, enhance plus 20 dB per decade. ठीक है ये?
Yes, sir. Thank you.
So till the magnitude of the pole is, if it's clear, then we can say what about the magnitude of the 0 is clear. What about the pole then? The pole will follow the same thing as a 0, but In case of a pole, instead of having a plus 20 dB decade, we are going to have a minus 20 dB decade. Okay, so instead of increasing, we are going to have a decreasing effect. And also before any frequency, before omega p, still it's going to be a 0 dB. Let me write the expression again for which this plot is. So this plot is for this one only a 0, which we just did, 1 plus pi omega z. Okay, 20 log. Whereas this plot is for the A of W, which we just write the expression 1 plus omega pi omega z divided by 1 plus omega omega p1. Okay, so this is omega p2. And one consideration which is given to us, that omega p2 is greater than omega z. Yeah, omega p2 is greater than omega z, and omega z is greater than omega p1. And for simplification, we just did this assumption. Omega z is equal to 100 times omega p1, and omega p2 is equal to 100 times omega z, right? So now if we want to do the Bode plot, we will start with again any frequency. We don't know this point, but we know that still it didn't reach omega p1, omega z, or omega p2. So, and we are not told about any DC gain, so we can safely start with a 0 dB. Okay, so we start with a 0 dB. We will continue to the 0 dB until we reach a point omega p1. As we reach the point omega p1, it will start decaying down with a slope of a minus 20 dB per decade. It will continue this minus 20 dB per decade until it reaches the point omega z. So this is omega z point. So as soon as it reaches the minus 20 dB per omega z point, the minus 20 dB per decade will in reality meet a slope of a positive 0.20 dB per decade. But this positive 20 dB will be cancelled out with this factor of minus 20, and ultimately we will be left only with this 0 dB per decade. Okay? So that is very much important. We are having a one pole which started at omega p1 with the negative slope of minus 20 dB per decade. The point where it met the omega z, the minus 20 dB per decade meets the positive 20 dB per decade, and it cancels out, and we have again a straight line of a 0 dB per decade slope. So there is no slope, but it has reached some value. Now this value is not 0 dB, it has reached some value which we don't know because we are not putting the exact numbers. But what we are sure now, it's a flat line with a slope of, let's say, 0 dB per decade. And we'll continue to have that slope until we meet a next pole, which is omega p2, and as it reaches omega p2, again we are going to have a minus 20 dB per decade, and it will continue forever until it meet a 0. Okay, so this pole effect was cancelled by this 0, for example, and then this pole effect was not cancelled because there are two poles and one 0. So net the slope is going to be minus 20 dB per decade if you want to set a very much higher frequency. Any question about the magnitude plot? Like, I guess this is all what we are going to cover for magnitude. Really?
Sir, could you explain कि ओमेगा z के ऊपर 0 dB by DEC क्यों होता है? Like यहाँ पर slope 0 क्यों है? हालांकि वैसे के थोड़ा diagonal है. Could you explain the slope?
Yes, 1 second. So let me just draw again a little bit omega for this is, let's say, omega p1. Okay, and this is omega z. ठीक है, मैं दोनों को separate draw कर देता हूँ, so then we can just see. We start, let's assume it was starting from this point and it was going, okay, so minus 20. यहाँ तक clear है कि this behavior is fine? We have one omega p and we have one. Ji Ali, till your hand is raised.
No, I'm clear, sir. Thank you. I
So
forgot to lower
now
my
when
hand.
we add these two together, we are going to have that resultant. So it will till omega p1, we are going to have this point, and then we will start decaying until we reach omega z1. Then we are going to have this. Okay. So that's why they canceled out each other plus and minus, so we have 0 dB per D. So normally we say the pole effect is cancelled by a 0. So now, since we have seen the magnitude, the main thing which we need to talk is the phase response. Okay. So for the phase, going back toward the same stuff where we have angle of AZ omega. So let's talk first about how the zero phase is going to come. We can just write in the form angle 1 plus j omega by omega z, or we can write tan inverse of omega by omega z. Okay. So we can write this expression in order to find the angle. Now we know, all of us know, tan inverse of omega by omega z is going to be, if omega is very much less than omega z, the tan inverse of this is going to be 0. If you just plug it again 10 times, expression 1 over 10, in reality it's going to be 4 degree, but for our simplification we are approximate to 0, so tan inverse of 0 is going to be 0 degree. When omega will be equal to omega z, tan inverse omega and omega z are going to be cancelled out. So we will left with 1. So the angle is going to be 45 degrees. When omega is very much bigger than omega z, for example, infinity, tan inverse infinity is going to be 90. If we just assume for our measurement a factor of 10, it's going to be 88, 87 degree. But for our simplicity, we assume anything bigger than factor of 10, we will take it as a infinite, or we will take it as a 90 degree. Anything equal to z is going to be 45 degree. Anything less than 10 times is going to be considered a 0 degree. But in the case of angle, the it's not continuous. It's not like a slope. It's going to continue. It's only for one pole or one 0, we are going to have maximum 90 degree. For the case of 0, it's going to be plus 90. For the case of pole, we are going to have minus 90. G, any concern? So if there is no concern, we can move towards next one. But let's just one thing clarify. In case of a pole, this plus 45 degree is going to be minus 45 degree, and this plus 90 is going to be a minus 90 degree. Okay. And the rule of thumb which I was talking is just here, that when I'm talking about omega less than, very much less than omega z, we are assuming a factor of 10 just for simplification. And when I'm talking about omega is very much bigger than omega z, I'm again assuming a factor of 10, but omega is equal to 10 times omega z. So just to mimic both things together, this was our magnitude plot, which we just did. Let me write the expression for which we are doing here. So if we see this one, yeah, I guess that's rather this one. Yeah. So if we see, this is the A of omega for us, and for this A of omega, this one is the magnitude plot. You can see the magnitude plot starting with a 0 dB for any frequency until it reaches the pole omega p1, which is known to us that omega p1 is the lowest frequency pole. So minus 20 dB decade starts. So as the minus 20 dB decade starts, it will continue with a slope of minus 20 dB until it reaches the point omega z. So whenever it's going to reach the point omega z, minus 20 is going to be cancelled out by plus 20 dB. So ultimately we are going to have a flat response of 0 dB per decade, and it will continue to have a flat response. Pole is going to cancel the 0 until we reach another pole, the second pole, at which again a minus 20 dB per decade is going to continue. So this is the overall magnitude response. Now we see correspondingly the phase response, and that's the way we normally do for the stability analysis. We draw magnitude response in relation to the phase response. So I'm directly drawing the phase response matching with the magnitude response. So I draw the same thing, omega p1, omega z, omega p2, and I'm also marking this time those factors that this point, for example, is 1/10 omega p1. This time, this factor is 10 times omega p1. This time 10 times omega z. This one 10 times omega p2. And if you remember, I previously write this also, this expression that omega, for example, for just our simplification, omega z is equal to 100 times omega p1, and omega p2 is equal to 100 times omega z. This is just for our simplification, so we can also have a nicer look in journal. Right. So if we see that we will continue with the 0 degree until we reach the 1/10th of first pole. So we'll continue with the 0 degree, and once we reach, so once we reach the 1/10th of omega p1, we will start decaying down with a slope of -45 degree. So we per decade. So we start with a -45 degree from here, and we will have an angle of -45 degree at omega p1, because at omega p1 tan inverse 1/1, we are going to have -45 degree. So it's going to be a -45 degree, and when we are going to reach 10 times of this thing, meaning for us tan inverse of, for example, infinity, in reality it's going to be tan inverse of a 10 or a bigger number, so we'll say it's going to be infinity, we are going to have an angle of -90 degree. If you want to do accurate, you can do accurate, it will be -88, -87, but for our simplification, we will stick to -90 degree. So we reached here, but once we reach here, this point is also what? It's the same thing as 1/10th of omega z, since this is a factor. So 10 times of omega p1 is equal to 1/10 of omega z. How? This is the same thing. Okay. So since this is the point, so since the omega z effect starts coming, we are going to see a positive trend, a positive 45 degree per decade, and it will start this positive 45 degree per decade until it reaches the omega z point. So at omega z point, it's going to be -45 degree, because that positive slope of 45 degree will add up here, and again it will continue till the point 10 times omega z, where it will get saturated. Now the pole effect is completely cancelled out by 0, you can see at this point. But once we reach this point, again we have a second pole, which effects start happening. Why? Because of this thing. This point 10 times of omega z is equivalent to 1/10 of omega p2. So this point, the second pole will start behaving. So we are again going to have -45 degree per decade. So it will reach, and at omega p2 again we are going to have an angle of -45 degree. At 10 times of omega p2, we are going to have a -90 degree. And after this, there is no effect. We are going to continue an angle of -90 degree. Since the first pole effect was cancelled by the second 0, and this 90 degrees is coming because of this second pole. Okay. So this is normally a phase response. We will see another example, but if there is some concern, some question, we can take it now.
Sir, can I ask a question? So could you explain the effect of 0 in this case at point of -90 at 10 omega p1? You said that 45 degree was being added due to omega z. Could you explain this statement again? I was unable to understand this part of the graph.
I guess this might be again better if I can draw on a separate paper. I will draw separate. All of them might be then a bit more clear. Normally, because this scenario was relatively simple, when we do them separate for practice and you can move on. Okay. So let's say this is the thing, and what we are given to us that omega z is equal to 100 times omega p1. So this point is 10 times omega p1, and the same point, which is 10 times omega p1, is equal to 1 over 10 times omega z. Okay. This is a 0 degree, this is a 0 degree. So if we talk about pole, the pole starts from 1 over 10. It will go at the frequency of this point at minus 45 degree and at this point of minus 90. So it will go like this. Okay, and then it will go like this. So if this is going to be a response of a single pole. If we talk about the zero will continue this thing till 1 by 10 z. This is 10 times. So it will go towards this point at 45 degree and then again a 90 degree. Because it's a 0, so it's going to be, trend is going to be on the positive side, so positive angle. So it will continue till 90 degree at this point. Okay, and then it's going to be a 90 degree. So now we just have to add both of them together. The same way we were adding the magnitude, we need to add them together as we have separated this. So if I add both of them together, at this moment I'm not adding the third pole, so I'm just adding these two. So again, it's very much important to write them. And again, one important thing which we were just writing, that 1 over 10 omega z is equal to 10 times omega p1, which is the point I guess Ali, you were asking, that this point 10 times of omega p is equivalent to 1 over 10 omega z. So these 2 points, these 2 points which I'm pointing at this moment, they are same. 10 times of omega p1 is equivalent to 1 over 10 of omega z. This means the pole of this first vector will continue to enhance till 10 omega p, and it will reach the value minus 90. So we are not going to have any issue until it reaches this point. So it will reach safely at a value of minus 90 degree. Because there is no zero effect coming. Zero effect will start coming as we move after 1 over 10 omega z. And this point is of 1 over 10 omega z. So after this, the zero will start playing its action. So after this, the zero will start doing this action. And it's plus 45 degree per decade. So if you see in one decade, this is 10 to omega. This is also, this point is 1 over 10 omega z. So simplification, they are same things. So it will start increasing from this point and will go here and will continue to this point. So this is minus 45 again, and this is 0 degree. So we are just adding this 1 and this 2 together, and we are finding this net third plot. Is it clear? Or there is?
Yes, sir. Thank you.
We'll do one more example. Might be, if something is still not clear, we can just get this thing. So the next example is from your book. So your book is doing a 1-pole system, 2-pole system, and 3-pole system. So I'm just putting like an example of a 1-pole and a 3-pole system and seeing how the response is going to be. So 1-pole system meaning we just have a 1 pole, and 3-pole system we just have 3 poles, meaning we don't have any zero. So we're not discussing about the zero effect. Correct? So if we do the magnitude response, it's shown here. At any frequency omega p1, we are going to have 20 log of h, which they are giving. At point omega p1, we are going to see a slope of minus 20 dB per decade, right? So if we want to draw the correspondingly phase response, it will start again at 1 over 10 omega p1. It will start decaying down until it reaches omega p1, the angle is going to be minus 45 degree. And when it reaches 10 times of omega p, the angle will be minus 90 degree. And once it reach minus 90 degree, it will stay here. Why? Because single pole system maximum gain, maximum angle which we can have, or phase which we can have in a single pole system is minus 90 degree. Okay, that's something we all should know, that for a single pole system, maximum phase we can have is a minus 90 degree. Okay, so that's this one. Then if we talk about a three pole system, so three pole system, we have omega p1, we have omega p2, and we have omega p3. So if we talk about these three poles, at the start of the first pole, we are going to see a decay of minus 20 dB per decade. So it will continue to have a minus 20 dB per decade, but as it's going to reach the point omega p2, we are going to have a minus 40 dB per decade, because after this there are going to be two poles. First pole effect minus 20 dB and the second pole effect minus 40 dB. So if you see the slope become a little more steeper, so it's going to be a minus 40 dB per decade. It will continue to have a minus 40 dB per decade until it reaches the omega p3, which is the third pole. So after a third pole, the response is going to become further steeper, and we are going to have a minus 60 dB per decade. Right? So this is the magnitude response of a three pole system. So it will continue after the third pole to have a steep response of minus 60 dB per decade. Now, if we draw the correspondingly phase response, so the correspondingly phase response will start by 1/10 of omega p1. Okay, so it will start with a minus 45. G. Josefa?
Sir, the magnitude plots that you plotted, where do they start from? मतलब वो y-axis पे कहाँ से start होते हैं? 0 dB से?
It depends upon.
Yes.
Yeah, if you have given a DC gain, then you will start with that DC gain. So that's why in this plot we are writing 20 log of h. So assuming there is some DC gain in the system. Okay, if there is no DC gain, then you can start with the 0 dB. Okay. Okay, sir. So it's the same DC gain. If you remember when we were doing an amplifier, the K or the DC gain, GMRO. So this is the GMRO. So at any zero frequency, we are going to have a gain. So we'll start with that gain. If the gain is not given, you can safely start with the 0 dB.
Okay, thank you, sir.
Right. So if we talk about the phase response, so in the phase response, again, we are going to start with the 1/10 of omega p1, which is the first pole, and we are going to start with a minus 45 degree per decade. At omega p1, we are going to reach a phase of minus 45 degree, then we will reach a minus 90 degree, and after minus 90 degree, it can flat if there is a more separation between omega p1 and omega p2. But if we assume the same scenario which we were assuming before, that omega p2 is equal to 100 times omega p1, or omega p3 is equal to 100 times omega p2. Okay, so if we do this thing, then we'll continue from this point, and we are going to continue with a minus 45 degree. So the slope here is constant, minus 45 degree per decade. Not as in the magnitude, the decades start adding. Since we are ensuring this thing, omega p2 is 100 times of omega p1 and omega p3 is 100 times of omega p2, the slope will all the time minus 45 degree per decade. Okay, again, just for the simplification we are doing, we can have the start like if you have, for example, omega p2 is equal to 10 times omega p1, then for some small instance you will have a slope of minus 90 degree per decade. But in this current scenario, for all of them, since we are meeting this criteria, the slope is minus 45 degree per decade until you reach the point 10 times of omega p3. When you reach the 10 times of omega p3, you will have an angle of minus 270 degree. And that is the maximum angle you can reach in a three pole system. Okay. So this is a three pole system in which we are assuming that omega p2 is equal to 100 times of omega p1 and omega p3 is 100 times of omega p2. G. Ali?
Sir, just wanted to confirm one thing कि omega p1 के first point के बाद second pole start हो रहा है.
हाँ सेकंड पोल क्योंकि हम लोगों ने ये रखा हुआ है कि
minus 90 degree से पहले
it's like this. Let me just is 90 degree पे ये touch होगा and 90 degree is the same thing which is 10 times omega p1 which is also equal to 1 by 10th of omega p2. तो वही जो कंडीशन हम पहले भी मीट कर रहे थे कि 10 times of omega p1 is equal to 1 by 10th of omega p2. ठीक है, इसीलिए as it's finishing here, next pole effect starts dominating. So overall the slope all the time in this scenario is minus 45 per degree. Slope is all the time minus 45 degree, meaning कि हर जो slope आपके पास एक 10 times decade में आ रही है, that is minus 45. The slope is constant in this plot because of this condition जो हम लोगों ने यहाँ assume की हुई है, ये वाली. ये clear हुआ point? So what I can do is some, yeah, if you think it's not a little bit clear, I can just draw a little bit on the scale using a scale and I can just share, or you can also look in the book because this is the example is 12.35 of your book. You can also look into it. If things are not clear, you can just tell me. I will just do again a paper pencil with lines so you might be able to understand more properly. Okay? Might be since we are going to do a couple of more examples in today's class or in the next class regarding the feedback. So the things might get clearer if they are a little bit vague now. If there is no question on this topic, we can just move towards the stability part because until now we were just reviewing the Bode plot. We didn't discuss the stability, how to decide a system is stable or not. Ali, your hand is still raised. Is there any concern?
No, sir, I forgot to raise my hand. Lower my hand.
Right. So till now we have seen the Bode plot, but we didn't see how the Bode plot is going to help us. So for that one, we again go back to our basics. And for that basics, we need to draw the feedback system. So this was the feedback system from where we started. We have an input Vs. It's going to, you can say a mixer, for example. And mixer is taking the addition of this Vs and the subtraction part from the output. And then this is going to Vi. And the Vi is going to gain A, and then it's going to a V out. So here is a negative feedback path going from an output, and this in output which is going to this mixer is known as Vf, and the other side is going to go Vs. Okay? So that is the overall feedback system. If we just want to write the expression, we can write the Vi, which is here, is equal to Vs minus Vf. Since it's a negative feedback system, so we can write Vs minus Vf, right? And also we can write this Vf, which is a feedback path. Vf will be equal to beta times V out. Okay? So we can also write this thing. Let me use a different color to identify. So this is one equation. Let's say A, and this is another one, B, in terms of Vi and Vf. And also we know that V out is equal to A times Vi. This is a feed forward path. So A times Vi is still our feed forward gain. So we can write V out is equal to A times Vi, or we can also write Vi is equal to V out by. And what we are concerned here, we are concerned to find the relation of V out with respect to Vs. That is our concern in the form of gains, the feed forward gain and the feedback gain. We are not concerned with Vi, which is an intermediate node now for us, and also Vf. So we want to get rid of Vi and Vf, and we want to represent V out by Vs, which is the overall gain of our system, because that is an input Vs and V out is the final output. And we have a feed forward gain A and feedback gain V. Okay. So what we are going to do in the equation, which is written as B or a 0.1, we are going to replace Vi with this relation, also Vf with this corresponding relation. So we are putting these, plugging out these things here. So if we plug out these things here, V out by A is equal to Vs minus B times beta. And if we just do a little bit left hand side and right hand side manipulation, we are going to left out with V out into 1 plus A times beta into A times Vs, or we are going to have this expression. V out by Vs is equal to A times 1 plus A into beta, or we can say feed forward gain divided by 1 plus feed forward gain multiplied by feedback gain. ठीक है? So this is the overall gain expression. A is the again the feed forward gain, or commonly we also known as open loop gain. AB is the product of feed forward gain and the feedback gain. We commonly also call it as loop transmission or a loop gain. Both of them are very much important, and that is going to decide the stability of the system. Anyone have any question related to this expression for the feedback? Okay. So now we have this expression of A divided by 1 plus A beta. What will happen if this G Nazish? Nazish, can you unmute?
I had a question in body plot. Sir, I had a question.
जी 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 बताएं.
सर जब हमारा दो पोल्स के दरमियान डिस्टेंस इज सच दैट 1/10 of omega p2 and 10 times omega p1 they overlap.
ठीक है. Okay, we can take one example of that one. So just draw the scenario, and if you think this is not the scenario you are asking, so we can change it. Okay. So for example, let's take omega p1 and omega p2. So instead of जो हम लोग पहले condition रहे थे 100 times, they are like 10 times apart. Okay. So we'll see the effect of magnitude में नहीं आएगा. Main effect is going to come on the phase response, but we will draw both. So what you are saying, if omega t2 is equal to 10 times of omega p1. Okay. So let's try to draw this one. This is the magnitude and this is the phase response. We'll just draw a little bit far. And this one is now also equal to 10 times omega p1. And this one is equal to, let's, for example, say 1/10 omega p1, 1/10. Okay. So that is something which we are mainly concerned, and also another point 10 times of omega p2. So हमें अपने जो 4 points चाहिए थे, we got those 4 points. So if we want to start with the magnitude one, magnitude might be a little bit easy. Again, start assuming we are starting with 0 dB. So we'll start with the 0 dB. Okay, until we reach the frequency omega p1, we will have a minus 20 dB per decade here. Okay, so we have a minus 20 dB per decade here. We will, since the point where we reach omega t, whatever its value, after that we are going to have a minus 40 dB per decade. So for magnitude, it doesn't matter wherever the omega p2 is going to come. If the omega p2 lie on top of omega p1, we are going to have a minus 40 dB. So for the magnitude response, we are safe. We don't have to worry much. It will continue all the time. But what will happen with the phase response? Let's see. So since 2 poles, maximum we can have minus 180 degree. So if we start with this angle, we will start with 1/10 omega p1. We will continue this point till this point. This is minus 40 degree, 45 degree per decade. Okay. So we'll reach this point. But now interestingly, अगर हम इस point को देखें omega p1, ये क्या कौन सा point है also? Omega p1 is also equivalent to 1/10 omega p2. अगर ओमेगा P1 में ओमेगा P2 का यहाँ से इफेक्ट ना आता, we will have minus 45 degree per decade. But since we are going to see the effect of omega P2, क्योंकि वो भी 1/10 में आ गया है, we are going to have a minus 90 degree per decade, right? So we are going to have a minus 90 dB per decade until we reach this point. So we are going to have this point. This is going to be until omega P2 पे हम पहुंचेंगे. And this is going to be minus 90 degree per decade until we reach minus 135. So when we reach this point, what's going to happen? We are done with the effect of omega P1. क्यों? क्योंकि this is 10 times of omega P1. After that, the omega P1 it becomes minus 90 degree. अब उसका कोई further slope नहीं होगी. After this, we are only left with the effect of omega P2, which is again going to be minus 45 degree per decade. अगर मैं इसको यहाँ point कर दूं, this is the point 10 times and it will reach to minus 1. अगर मैं इसको point out करना चाहूँ, this is only effect of omega P1. This is effect of omega P1 and omega P2, and this one is only again effect of omega P1. Is it clear?
Yes, sir. So now we were talking if in this response, which is V out by Vs is equal to A times 1 plus A multiplied by beta. Okay. If, for example, A times beta, which is a loop transmission gains, becomes minus 1, what will happen? If this product becomes minus 1, what's going to happen? 1 minus 1 is going to be 0, but it is in the denominator. A by 0 infinite. So if 1 plus AB equal to 1 minus 1 equal to 0, this means V out by Vs will be equal to A by 0, which means infinite. Whatever the gain, the open loop gain we have, very much small, very much big, doesn't matter if this factor A times beta becomes minus 1. What's going to happen? My gain is my overall output gain of the feedback system, that is the net gain going to be seen by my input, is infinite. My system is become unstable, and that is something we normally call an unstable system or oscillatory system. We don't want this thing to happen, or the system is becoming a positive feedback system. That we have to avoid, and that is the condition for stability. Okay. So V out by Vs is become A by 0, become infinity, unstable system. And that is the definition of an unstable system in a feedback or in a negative feedback. Since the negative feedback system, somehow because of this value of A times beta, if it becomes a negative one, instead of having a negative feedback, now the system becomes positive feedback. This means system becomes unstable. Okay? We need to do something how we can get rid of it or how we can judge this condition from the Bode plot. At this moment, we just saw this is the equation. If A times beta becomes -1, well and good, it becomes an unstable system. But how we can find from the Bode plot, from the magnitude and the gain plot, let's see this now. So, yeah. So this is just a simple depiction. What's happening at time t is equal to 0. For example, we have any factor, any noise. For example, this omega 1 is a noise, very much small noise. We're not much concerned about the noise. It's in the picovolts range, very much small. It's coming to our system, which is a closed loop system. It's passing through our transfer function h of s. Red one is at time t2, so let's only talk about t0. So t0, this is going to pass through it. It will pass through a negative feedback system, k, which is a negative feedback system, multiplied by some factor k, and will add up here. Well and good. But what will happen if this h of s or the overall this h of s and k, product of h of s and k, has 180-degree phase? What will happen to this response? It will become out of phase. If this was like this, the response is going to be 180-degree phase shifted.
And that's where the -1 terminology is coming. We have a system which is just giving a simple sinusoid, but when it passes through the product of h of s and k, it changes its phase. It becomes 180 degree. And when we are going to subtract these two signals, since now the phase becomes 180 degree, instead of subtraction, they are going to add up together, which you can see in the red line. So the signals become amplified. It's going to pass through it. The signal is going to be amplified and we are going to have a bigger signal. Next round, again, this phenomena is going to happen. And this will continue to happen and signal will continue to amplify. And ultimately, the signal becomes amplified or infinite. Or if it's an amplifier, it's going to be saturated, maximum voltage. We are not going to get any useful signal. So for a very much infinitely small input noise, if the system is unstable, if the closed loop is unstable, the system is going to be distorted. That's what we don't want. And what is this condition of -1? If we want to talk in the form of magnitude response and a phase response, this is a +1 magnitude with a 180 -180 degree phase. अगर आप इसको log में scale की बात करें, 20 log of something, if it's 0 and if the phase is -180 degree, this means the system is unstable or it's equivalent to -1. And this is the main condition for stability. That's why the Bode plot is very much helpful to see both magnitude and phase together. So the magnitude is telling us the value of the magnitude when it is 1 or when it's not, and phase is telling us what is the phase. At this moment, for example, for two-pole system, we can have a -180 degree. Ji Ali?
Sir, could you repeat after what you told regarding infinite gain,
Okay.
representing instability? उसके बाद से जो आप इस point -180 तक आए हैं,
ठीक है.
इस part को explain कर देना.
So this from this point, right? -1 is okay for everyone.
Yeah.
ठीक है. So if we're okay with the
Yes.
-1, now we need to represent this -1 or k times h j omega in terms of a magnitude and phase. -1 है क्या हमारे पास चीज? Can I write this -1 is same thing as 1? अगर आपको याद हो, can you write this thing? +1 with an angle of -180 degree. Is it same thing as -1? क्या आप लिख सकते हैं इस तरह इस चीज को? And that's where we are representing it. आपके पास क्योंकि मैग्नीट्यूड जब आप बात करते हैं मैग्नीट्यूड रिस्पांस में, the value is absolute value. There is no sign. All the values are absolute, meaning they are going to be treated as positive. But the phase is going to tell us whether the value is positive or negative. If I am having a -1 and I need to represent in the polar coordinates, meaning I need to represent in the angle form, and the magnitude is going to be 1 and the phase is going to be -180 degree. And that's what we are depicting from the Bode plot. And we reach to this point whenever in the feedback system, the product of k times closed or the loop transmission gain, for example, the feed forward and the feedback gain product loop transmission is equal to -1, the system is unstable. And from the Bode plot, when it's going to be unstable, this means whenever my magnitude is 1, magnitude response value is 1, and the phase response value is -180 degree. Okay? Or anything bigger than -180 degree. Is it clear? So we have some depictions, I guess, that we might start today or we might have in the next lecture. But just at this moment, the condition for stability is this one, that the overall magnitude response in terms of dB is going to be 0 and the phase response should be -180 degree. We have pretty much now further illustrations which we can use it, but what I would highly recommend that we can continue from this point in the next lecture, and I will upload these pages for your visualization, and we can just come and we can discuss about the stability, and we'll do a couple of examples. So we can just take 40 minutes and 45 minutes to wrap it up in the next lecture. Okay. since we will have also the quiz. So I guess that's a nice point to stop here, and we can have the quiz in the next lecture, and we can just cover before the quiz all of this content. Any concern, any question? Then I will, GLE.
सर regarding the quiz, sir, quiz किस time पर होगा और वो
जी,
online होगा, scanned
मैं
होगा, कुछ explain
right, yeah. So the quiz, what we are planning to do, we will start the quizzes at 2:45 p.m. on Wednesday, next lecture. So we will give you the, at 2:45, we will share whatever the quiz you have to do on your paper and pencil, and you will finish your writing, and you will scan it, take a picture and upload on LMS. Okay, and you will have overall a window to finish that whole activity, let's say by 4 p.m. Okay, so you can have 1 hour and 15 minutes to finish that activity, to ensure all of you who have limited internet connectivity and all the stuff. So the quiz will be hardly for the same way as we normally do, 15 to 20 minutes, but the other time span is just to ensure that you try to, you have facility to upload and do the scanning and all those things. Okay, so it's better once you are done with the quiz, write the time which you have taken, and you just upload that. We will just share the instructions, a couple of lines by the end of today, at what's going to be expected from all of you. Okay?
So what is the syllabus would be told
Syllabus
later?
will be before today's lecture. Okay, so before today's lecture, meaning the stability will not be included before you cover 2 lectures with Dr. Wala, those lectures will be included.
Okay, sir. Thank you.
So any other concern or any other question related to today's lecture? G. Shahzain.
सर ये जो ऊपर आपने सर्किट बनाया और इसमें जो सिग्नल से कॉरेस्पॉन्डिंगली आपने एक्सप्लेन किया था, कैन यू प्लीज डू दैट अगेन?
Can you just again say, because I just can you say again a little bit loudly?
सर जो सर्किट बनाया हमने फीडबैक लूप का ऑन दिस पेज
जी,
एट द वेरी स्टार्ट ऑफ दिस पेज
हम्म,
वाज सर इसमें जो आपने सिग्नल के थ्रू थोड़ा एक्सप्लेन किया था वो जरा दोबारा कर
ठीक है,
सकते हैं?
मैं दोबारा ड्रॉ कर देता हूँ, then it will be easy to follow up. ठीक है, तो so what I was saying, that initially, if you have any signal or omega 1, for example, it was coming of a noise, okay, a sinusoid signal. If this signal is going to come here, the signal will add up here, will come at here in the first time t is equal to 0. If we just talk about everything is at time t is equal to 0, for example, at one time instant. So the signal will come here, the signal will pass through this transfer function, whatever it's going to do, it will come here. But this same signal will reach here. It will go definitely to V out, but we are concerned what's happening after one feedback system. So it will come here, it will pass through this K. So now what I was saying, if the product of HS and K is equal to -1, or what it is doing, if it's doing a 180-degree phase shift, what will happen to the signal? The signal will become 180-degree opposite. Now this signal, which is coming here, will add up together with this signal. Previously it was subtract, but now because of this phase shift, ultimately they will add up together, and the signal which we are going to have, it will be a little at t times equal to t1, will be a little bigger. The signal will again pass through this one, whatever the transfer function will do it here, and we have an amplified version here. This amplified version will again pass through this feedback path. This feedback path will again pass through h of s and k, and we have a bigger amplified version, but again out of phase. Subtract again the signal which we are going to have at t2, a bigger signal, and the bigger signal will reach up here as a very much amplified. So this time will continue. So after, let's say, you can assume t is equal to 10 times of t, this thing, the signal is going to be very much amplified, and we might not able to recover that signal, or we might not able to see that, because by that time the amplifier has already saturated. Saturated mean it reached the maximum VDD value. So we cannot recover the signal, or what we are only going to get something like this, which is VDD here, a square pulse, or signal was somehow a small signal, or the system gets saturated. Okay. So normally there is the same mechanism of any positive feedback system. So there is instead of having a negative feedback, a positive feedback is going. So अगर negative feedback होगी तो signal will get small, like signal अगर इस तरह था, then it will become like this, then it will become like this, then it will become like this. But in case of positive feedback, it's going to enhance. Okay. Any other concern? So I will just share the lecture as we normally do, also on LMS, also on YouTube, and also will share the handouts which we wrote also on. Ji Bilal. Ji Bilal.
Yes, Assalamualaikum,
Bilal.
sir. Sir, stability की condition आपने क्या कही थी? वो repeat
Stability
कर दीजिए
condition
सर.
के लिए it should be k times h of s should be equal to -1. अगर ये -1 होगा तो this means system is unstable. In terms of magnitude and phase response, we are talking that both of them should be that magnitude should be 1 and phase should be -180 degree. Just one second, I will bring the charger for my laptop. Getting it.
Bilal, HFS k equals to 1 या -1 condition है stability की?
-1 कह रहे हैं सर.
HFS of k equals to -1
Unstable.
होगा तो stable होगा system. Unstable होगा.
अगर 1 होगा तो स्टेबल होगा.
जी मैम, जी आप बताइएगा. It's not only
Yes, sir.
k, we are talking about the combination, like multiplication of h of s by k and k.
सर ये -1 है h of s multiplied by k या 1 है
नहीं,
for
just
stability.
मैं लिख देता हूँ. Let me just. So h of s times k, अगर आपके पास -1 होगा, then the system means it's unstable.
Okay.
ठीक. Now we represent this thing with the help of a Bode plot. We say कि अगर h of s dot k का magnitude response, this is a magnitude response, ठीक है, 20 log is equal to 0, और या खाली जो magnitude लिख रहे हैं हम equal to 1, and phase of this one again product, ठीक है, loop transmission gain equal to 180 degree. Both of these things mean system is unstable, and both of these things are same.
-180 degrees, right?
जी. ठीक है.
ठीक है सर, thank you.
Okay. We will continue from this point. So अगर आप further कोई queries होंगे, definitely we can take in the next lecture. ठीक है. But I would highly recommend, अगर आप 2-3 nice scenarios हैं which we are going to talk in the next lecture about the gain crossover and the phase crossover, if you can just go through, it will be very much. Any other concern, question? If there are no further questions, we will just stop here and we will continue in the next lecture from the same point. And what we can do is just for those students who have like a class at 3:30, the quiz in reality is a small quiz. It's not a long quiz. It's just like going to be like a 15-20 minutes, the same as in class quiz. The extra time we are only giving to those students who needs like who don't have stable internet connection or who have some other issues. What we can do, we can start the quiz at 2:30, but then it's not going to be much helpful. I would like we stick to the 2:45 point, and you will have sufficient time. If there is a class at 3:30, you will have 45 minutes to finish the quiz, and that's more than enough. As I'm again saying, quiz is not going to be more than 15-20 minutes. We will share the instructions for the quiz by tonight, that you have to write how much time you spent on the quiz, because we want that you should finish that in 15 to 20 minutes, not more than that. The other time is just to ensure that all of you are able to upload. Okay, so we will share that instructions by the end of today. Any other concern? If there is any other concern, you can also send an email to us. We can also hold some extra sessions if needed. But for now, I guess we will close the session, and just hope we will meet again on Wednesday, and we'll cover the content and we'll also have a quiz. Thank you.